Good morning, good afternoon, good evening to all the participants joining this online seminar. Welcome to the third series of online seminar from Endress+Hauser. Today's topic of discussion, as you can see on your screen, is guided wave radar. Guided wave radar, it's a well-known technology. We have done a lot of things to make this technology perfect so that it fits several applications in oil and gas industry. We will start today with our basics on free space radar and guided wave radar, and we'll take a deep dive into most applications. Some of them are quite challenging, and those challenging applications have actually taught us to add some more features, and our speakers will go through it today. Can we go to the next slide, Matthias? Thanks. This online seminar are sponsored by Endress+Hauser. On the top right-hand corner, you see the picture of the headquarters of Endress+Hauser. We are a 14,000 employee company. Last year, we did a bit over 2.6 billion euro. We have a base of around 8,000 plus patents, which ensures that we are able to deliver innovative instruments for your applications and to solve your measurement challenges. In a physical seminar, we typically have a safety briefing. Considering the current situation, we would like to focus on safety around pandemic situation. There are certain things which are in your control, like wearing a mask, maintaining the social distance between colleagues, and also isolating yourself in case of symptoms, testing, tracing, and vaccinating if it's possible in your country, so that we can save our loved ones, our society, and get back to normalcy. Today we have with us Matthias Kaiser from our level and pressure factory, who you can see, he's actually not in a virtual background, he's really in the factory, and also Rob Vermeulen. And now I hand over to Rob. But before that, just a small housekeeping topic. The presentation which you will see right now, it's available as a download on the GoToWebinar platform. My name is Janish Gewala, and I will be your host for today's session. Over to you, Rob and Matthias.
Yeah, thank you, Janish. Small introduction of myself maybe as well. I have a funny accent from the Netherlands originally. They have funny accent. I will do some part of the presentation as well with regards to applications. I'm an electrical engineer and have some degrees in economics. I'm long-term with Endress+Hauser, started in 1993. And at the moment, I'm located in the United States, in Greenwood, where we have a production campus for North and South America. And that's where I'm normally located. I'm married. I have 3 adult sons. Now, I don't know when sons ever become adults, but anyway. And we have 2 cats, one called Leo and one called Pete. So that's me. I'm giving it to you, Matthias.
Okay. So I'm, first of all, welcome to Endress+Hauser Level and Pressure in Germany. So this is real, it's not fake. My name is Matthias Kaiser. I'm a business development manager within our factory for level and pressure devices for the oil and gas industry. And besides this, I'm also an area manager again for level and pressure. And I'm caring for the Middle East and also Germany. Yeah, the idea was to go to the factory today and make this from our factory, just to give you some other view than home offices, which I'm sure you see in quite some webinars these days. We are here actually in our validation center. So this is part of all the testing that we do with our devices already in the research and development phase. So you could call this also, this department here, as one of, or as the first customer that an Endress+Hauser level or pressure device will see in his life. What we do here typically is a lot of training of service people, but also of customers. And as I already said, we test a lot of devices here for our own purposes. And what you see is a lot of different devices. So you see some tank gauging radars. You also see a couple of process radars over there. And you also see a guided wave radar. And on the other side, some more, which you don't see. But this is our topic today. So it's all about radar technology. What's the topic there, and how does guided wave radar support you in your processes? And now I switch over to the screen again and take off my camera. Here we go. We've discussed this, and now topic is radar technology. How can radar technology support you? And what about radar technology in general? Let's have a short look at the technology and at the trends at the moment. So what we see in a lot of industries, also a little bit in the oil and gas industry, is that when we talk about free space radar, there is a trend towards higher frequencies. So this is the frequency with which we measure. In this case, it's 80 gigahertz. That is what I would call the latest trend in the industry, so also in the measuring instrumentation general for level. What's the reason for this? So the higher the frequency, the smaller is my beam angle. And if I have a smaller beam angle, I will not touch obstacles in a tank, for example. So this makes my life easier. It makes it easier to commission, for example. And since the focus is smaller, I can also go typically larger measuring ranges because I have a better focus, you could call it. But still, there are other measuring technologies, other frequencies. For example, in our portfolio, we also have 26 gigahertz, which is still a very good frequency for free space radar. So you could say this is suitable still in 80% of the cases of the application. So a very good frequency still. And there is the oldest technology on the left-hand side, which is 6 gigahertz. Yes, it is the oldest, but still there is a reason why we still have it in our portfolio, because this will typically solve the stilling well applications the best. And also if you have strong condensate in your processes or a lot of turbulences in your vessels, this is also the free space radar frequency to go to. And now if you come to real demanding applications, and we see a lot of those in oil and gas, but maybe also in chemicals, then we go for a guided wave radar, and we call this 1 gigahertz. Yeah, this is suitable for all the applications where you have a lot of foam or very low dielectric constants. I will come to this later. And also if you think about interface measurement, gas phases, or also bypass applications, this is maybe the #1 go-to device that we have here. Just to complete this slide, you see we just summed up all these different gigahertz frequencies, and we end up with our campaign slogan 113 gigahertz. The reason for this is we say that there is not just one frequency, but you need all of these different radar technologies to be sure that you can solve a customer's application the best way possible. And now if you think further, you can't even just think of radar itself, but you also have to, in some cases, use nucleonics, radiometrics, however you call it, or also capacitance probes. And this is what we as Endress+Hauser, this is very important for us, that we have all this stuff in our portfolio to be able to support you the best way possible. But today we stick with radar. Let's have a very easy overview how it works. So we have here our guided wave radar and our free space radar, and from this we emit an electromagnetic wave down to the surface of your water or your oil. And as soon as this electromagnetic wave hits the surface, there is a change in the dielectric constant. Because the dielectric constant, for example, for air is typically 1, for water it's around 80. And we need this change because this change will then reflect the wave, the electromagnetic wave, back from the surface up again to the device. And what we do then inside the device is actually that we measure the time of this traveling of the wave down and up again. And from this, we can then calculate the distance from the device to the liquid surface. And with this information, we can tell you how much level is in your tank. So, and now let's come, I mean, this is just very basic. If you want to learn more about the measuring principles, I can recommend you go to endress.com. There are measuring principle animations for radar. So there you learn a little bit more. You would also find this on YouTube if you want to learn more. Now let's come to our actual topic today, which is guided wave radar. We call it the problem solver, as we already said, or as I already said, especially also in the oil and gas industry. And why? So whenever there is bypass measurements, and we see them a lot in a couple of industries, we typically recommend guided wave radar. Whenever you want to measure an interface and you also want to measure the top level, for example, in a separator, you have the interface between water and oil, and you also want to measure the top level at the same time. This can only be done with guided wave radar or maybe with radiometrics, nucleonics, but guided wave radar is maybe the easier version to go to. We have reliable measurements, so we can go high temperatures, high pressures, but also low temperatures, as you can see. We have a so-called end of probe signal evaluation, which Rob will tell you a little bit more about. And in general, we have a strong signal because the signal is guided along the probe, and this makes it stronger, and you don't lose too much of your signal strength. And this helps us when we talk about foam in a process, when we have build-up, or if you have turbulent surfaces or also obstacles in the tank. And last but not least, there is something called the gas phase compensation, and I will tell you more about this later on. So these are the pros for guided wave radar. There are also limitations we have to admit. Whenever you have lateral forces, like you can see in this picture here, you have an agitator and the guided wave rod was too close to the agitator, then it just flipped around this agitator. Things like this can happen, so you have to be careful whenever you have an agitator. Think of going free space. Or also, if you know you have a lot of flow dynamics in a tank or in a vessel, then you should also think of going free space radar, or at least contact your Endress+Hauser salesperson to be sure that this application will work then. The other point is extreme buildup. Whenever you have too much buildup, you wouldn't want to put such a guided wave radar into the vessel, because this will just make your measurement wrong. There we would also say go for free space radar or also capacitance probes where we have our active build-up compensation integrated. So, and with this, I hand over to the applications.
Before Rob, you start speaking, just let me ask the guys if they captured something from what my friend Matthias mentioned. So there's a poll on your screen. It's a very simple question, and I think Matthias gave the answer to this one. What makes radar waves reflect? A change in dielectric constant, whatever that is, a change in density between product, a change in conductivity between products. And I would request that you can answer the question, become part of the community which has understood something. Yes, this is good. I would say last 15 seconds to go. Last 10 seconds. And I would like to close the poll with this. And I'll share the results quickly.
Look at that. Some people had learned something. It's a dielectric constant. Yes, that's completely right. Let me shortly explain what dielectric constant is, because a lot of people talk about dielectric constant, or one of those sales engineers from Endress+Hauser is asking, what's your dielectric constant, sir? Well, the dielectric constant is the property of any medium, solid, liquid, to polarize or to hold an electrical charge. So it's an electrical property of any medium that's called a dielectric constant. Now there is a lot of description in books about it as well, but if you keep that in mind, that's important. So don't think about density, don't think about conductivity, although they both have something to do with it sometimes, but it's dielectric constant. If you talk radar, you talk capacitance, you talk dielectric constant. So with that, I'm going to talk a little bit about the a very interesting and also very much used application in the oil and gas industry for guided wave radars, both offshore and onshore. And that's a separator vessel. So let's go to the separator vessel. Here you see a thermal image of a separator vessel. So on the left-hand side, that's where your whatever comes out of the hole goes into. The borehole, I mean, with that. So it's a mix of water, of sand, of oil. Sometimes there's also some chemicals involved there as well. And those chemicals, together with the oil and the water, can form an emulsion. So there's a lot of dynamics going on there as well. On the right-hand side, you see the weir, and over the weir on the other side, you see the oil. So you have a separator, separates the oil from the rest kind of stuff. And why do you need those instrumentation on top of it? Well, on the right-hand side, where the oil is, you want to measure the amount of oil that comes out of it, and make sure that the oil is not flowing back into what came in of it. And on the other side of the weir, you want to know how much is in there, and you want to make sure that also the water is not going over the weir into the oil section. Now, if you also want to measure the sand, and maybe also want to measure the emulsion on a continuous basis, I think guided wave is probably not the right technology to do so. Maybe you have to go to a combination of guided wave radar and capacitance, or nucleonics, so a gamma measurement system that can actually see through the tank wall from the outside and pick up all layers in a system as well. So next slide. Oh, and gas comes out to the top, of course. Now. So here you see a typical vessel. Yes, you have them horizontal, you have them vertical, you have them big, you have them small, all kinds of sizes, but the measuring principle is more or less the same. Where you see the guided wave radar on the left, and measuring the overall level and the level of the interface, so the junction between the water and the oil level, and the one on the right measures the oil level. So that's what you see here. And they even have some backup system, because nobody ever this mistrusts his eyes, of course, with the side glasses that you can see on the side as well. So next slide. So these are the typical situations what you normally have in these kinds of separator vessels. So you have a clear interface between water and oil. Now, yes, they do exist. Probably a little bit more in refineries than on the upstream applications, but a clear interface, so a clear cut between the water and the oil, you see seldom, very seldom, but they do exist. This is the easiest way to determine the different levels. So you get a reflection from the oil level on the top, and you get a reflection from the water level under the oil level as well. And you can determine the level of your interface and the overall level. Simple. Now, when you go to the second tank, the interface with the emulsion layer, what you see on your screen is that you see there is no real junction. Yes, you have a junction between the gas phase and the oil on top. Yep, that's clear. So you can measure the overall level, no issue at all. But then you have a gradual change from oil to water. So there is no real change. It's a very gradual change. It's not a jump. And it makes it very hard for guided wave radars to get any signal back, because where does it come back from? There's no jump. So if you have situations like this, then it's probably better to go to a capacitance probe for the emulsion layer, and you measure the interface, the overall measurement itself with a guided wave radar. But you have to have two holes, and that's not very great either. And then you have a third scenario, which you see on the way on the right, where you have and sand and water and emulsion and oil. If you want to measure that, please go to a nucleonic system or a gamma system and make that work. We can talk to you about that as well, but it will be a totally different seminar or a webinar to talk about that. So next slide. Can we go to the next slide, please? Yes. What you also keep in mind is, where does the oil come from? Now, why is that important? It's not so much about the properties of the oil, so the dielectric constant, but it has more to do with the API, or the specific gravity, so the stickiness that is of the oil itself as well. If it's very, very, very sticky, like you have API around 20 or something like that, so the heavy oils where you also have paraffin and wax buildup on rods, not sure if a guided wave radar is the best technology to use in those kind of applications. If you go to more to medium oil, light oil, condensate of course, then a guided wave radar is a perfect kind of technology to use for overall and interface layers. Now, what we do is, of course, that we put some Teflon coating on rods or on cables in order to make the rod or the cable more slick. So you do not have a lot of buildup of that wax and paraffin on the rod or on the cable itself. That will help it a little bit, but it will not eliminate the issue. So heavy oils, very sticky heavy oils, please be careful. Please be careful. Might look for a different kind of technology. Next slide. Now, what we did do is for a clear interface, like I said, use a standard guided wave radar. Very simple to solve. There's no problem at all. Next slide. But if you have an emulsion layer, like I said, please have a look at capacitance. A capacitance probe can determine, even when you have big emulsion layers, the average layer thickness of the interface itself, and together with a separate measurement for the overall level, you can calculate where the emulsion layer size is versus the total amount of level inside of the tank. So maybe their capacitance is a good one. So that gave us a good idea. So what we did is we developed a guided wave radar that actually has both a capacitance probe and a guided wave radar into one device. Can you imagine? So sometimes we measure a guided wave, and sometimes we measure capacitance with the same probe, with the same device, and you don't even know if the unit is working based on capacitance because it sees a big interface, big rack layer or a big emulsion layer, or no, I have a very nice clear cut and I can use my guided wave radar signals in order to determine the thickness of the interface. So either or, and we build that into one device. And that's called a guided wave radar FMP55. So with this, you only have one hole and can still use guided wave radar for the overall level, and it automatically switches between capacitance or guided wave radar depending on how your emulsion layer is being built up, and you don't even know it. So it's great, works perfect. Next one. Then what you might also not know is that we have actually a redundant measurement signal on a same probe of a guided wave radar. So normally we emit a signal from the top, a radar signal like Matthias in the beginning described. And when we have a change in dielectric between the gas phase, the air, and then the oil, you get a small reflection back, and we calculate the time and the distance. But what you do not know is that we actually have a secondary measurement principle on the same probe, and that's called the end of the probe signal. So if you look at your screen, you see a junction between the rod and air at the end of the probe. So the dielectric constant of the metal probe is sky high, and the dielectric constant of the air or gas phase where it's in is very, very low, around 1. So we have a huge jump, and that's what you see on that probe. You get a huge signal back. Now, what happens if you put some level on it? If you put some level on it, and it's, in this case, water, it gets a huge reflection back from the water, because the dielectric of water is around 80. Huge signal. Now, the end of the probe signal you probably won't see anymore because it's water. But if you have oil on top, which has a low dielectric constant, what you will see is what you can see on the screen here as well, is that you get a small reflection back from the surface, because the dielectric change between air and oil is only 1 to 2, but you get a huge shift in end of probe signal. And what the unit does, it compares the shift of the end of the probe with the level measurement measured, and it more or less compares the two to each other, so you have a backup system in case you have small reflections coming back from the oil itself or from a product which have a very low dielectric constant. Now, that also brings me to another point. If you get a small reflection back, that does not mean that the measurement itself is inaccurate. In general, if you get a small reflection back, whether it's on guided wave radar or on a free space radar, it is accurate. The amplitude of the signal itself is nice to have because it makes the signal more reliable and available, but it does not have to say anything about the accuracy of the level measurement itself. So please do not make the mistake that big amplitudes, high accuracies. That's not the case. Small reflections can have the same accuracy, or maybe even better. Who knows? Okay, so end of probe signal, a redundant measurement principle on the same device built in, and you don't even know if the unit is working on EOP, end of probe signal, or on reflection. The unit just gives a very accurate measurement reading. Now, this gives me one more thing. This end of probe signal, if you shorten the rod or the rope, you need to tell the unit you did so. Because if you don't, the unit is thinking out of the factory that the rod has a certain length. So the end of probe signal should be within a certain bandwidth. If you now took whatever, a foot or 3 feet off, then the end of probe is something else, somewhere else. So you need to tell the unit that you shortened or lengthened the probe. It's only pressing of 2 buttons. Have it determine its own electrical length again. You don't need to go in there with a measurement to determine the length of the probe. It just does it itself, but you need to do it when you do so, because it will help you get this redundant measurement principle working the right way. Next slide. Okay, do you have some questions for the audience, Jenish?
Yes, I will quickly send a question now. So the question goes like this: a small reflection from a radar signal is less accurate than a large reflection. What do you think? Is it true or false? And your time starts now.
I think it's a pretty easy one when you paid attention, Jenish. What do you think?
Yes, I paid attention.
That's a good thing.
Exactly. So you got last 15 seconds to go. And 5 seconds. Come on, answer it. Yes. All right. So I'm going to close the poll and I'm going to share the results.
There you go.
Rob.
Yes, people paid attention. Absolutely. Please never make that mistake. Oh, I got a huge reflection, got huge signal. It must be accurate. Always question that, because the way a sensor is being built into a tank is different than when it was calibrated or produced in the factory. with regards to the speed of how the radar propagates inside of a tank. A tank is smaller, has more walls closer maybe to the measuring rod than when it was calibrated, and all that stuff has an influence on the accuracy. Gives huge reflections, but always set it up in a tank or in a bypass when you apply the unit. Do not just stick it in and walk away. It works, but you don't know if it's very, very accurate. Okay, with that, I'd like to hand over to Matthias.
Thank you, Rob. Well explained, and the message was there. Nearly everybody knew it. Very well done. Let's go on with another application, another typical application that we see in the oil and gas industry, but we see it also in other industries for sure. And that's really a classic, the steam drum or boiler. Here you can see some examples. For example, here with a separate version of the transmitter head, here you have the probe inside the bypasses, and up there the actual transmitter head. Yeah, what's the point with boilers? You can have huge inaccuracies or errors in your measurement in a gas phase. Here you see an example. We talk about 300 degrees Celsius, and we see with a traditional radar, we see a deviation of 18%, and this can even go higher. We've seen higher deviations there. If you take a look at hydrostatics of loads, this is even higher. And now if you take a look at a radar with a GPC, you end up with 2%. Now you might ask, what is a GPC? And I've mentioned it before already. It is a feature. So if you order an Endress+Hauser level flex, this is our guided wave radar, with a gas phase compensation, you will get not only the standard rod, so that's the inside of the left-hand side guided wave radar, that's the inside. You will not only get this rod, but you will get a second rod on the rod, you could say. And this is a reference rod. And this is actually, besides a lot of software algorithms, the feature that you can directly see if you order a device with gas phase compensation. Yeah, this is a reference reflection that we create here, and you see it on this example there. So that's just the in-coupling signal, and then you see this small signal. We call it a negative signal because it directs in this direction. It shows in this direction, and you see this exactly where the end of the reference rod is, and we know exactly where the reference rod has to end. So we have a clear picture there. And then you see in normal conditions, so there is no steam phase or no gas phase here. So you see the level is also being measured correctly. We see the right level. Now, what happens if we have a lot of steam in there in this bypass? Here you see the steam, and now you take a look at the signals. This signal has moved downwards, right? It's not where it should be, because actually it should be somewhere around here. But the good thing is we know exactly where it has to be, because we know exactly by millimeter where this end of the reference rod is. By the way, you also see your level measurement is not correct anymore. It shows you actually way lower level than you actually have in the bypass. But thanks to this signal of the reference rod, and thanks to our knowledge in the device and our algorithms where this should be, we can actually calculate it back and compensate that. So we know where it has to be, and with this knowledge we can also calculate back the real level of the device or the real level in your bypass. And with this you have a way clearer, more reliable measurement in such applications. Gas phase compensation. Yeah. Where can you use it? Typically, steam boilers. Ammonia is a media that also causes a gas phase, and this gas phase, I didn't mention this before, this gas phases actually, they slow down the radar signal, and that's why you have a deviation. You can also have this with hydrocarbons at high pressure, and if you have the level flex with a dynamic gas phase compensation, this will just compensate for this gas phase every second. So it's not like it takes a minute to do such a compensation, but it's on the fly every time. So you really have a safe and secure level measurement also in such applications. This brings me to my next topic, because this is also a typical thing where we recommend level flex or guided wave radar when we talk about bypasses. And you will for sure have a couple of bypasses in your plants or in your applications. You know best when to use those whenever you have turbulent surfaces, for example. And here also level flex from our perspective gives, or a guided wave radar gives the best signal here compared to other technologies. Also compared to, let's say, mechanical level instruments like displacers or floats. So here we clearly recommend go with a guided wave radar. This will give you the best measurement. By the way, whenever you talk about bypasses and guided wave radar, for example, you need one, you can also get this whole package from Endress+Hauser, not just the instrument, but also the bypass. And you can then get this already packaged and pressure tested in our factories. So this is maybe also a thing to think of and also to discuss with your Endress+Hauser salespeople when they visit you and you need something like this. We can support you there too. Yeah, and then last but not least, when we talk about mechanical meters, and whenever you feel like, I mean, we had an example in Europe where we replaced a lot of mechanical meters with guided wave radars in a refinery. So this is pretty easy to do. In 80% of the cases, this is one-to-one. So if you have mechanical meter instruments in your plant and you want to renew them anyway, then why not thinking of a level flex or guided wave radar? It has some advantages. So you don't have an upper blocking distance. It is less influenced by buildup, independent of foam, more or less. You have no moving parts. Maybe this is one of the most important topics here. And you have things like gas phase compensation, like I've showed you before. And you can also do some other stuff, which you will now see on the next slide, which I like the most, some practical stuff. Cutting the probe. Rob already told you how it works and that it works, but don't forget, you have to tell the device that you cut the probe. That's the most important topic here. What you can also do with such a meter from, or with such an instrument from Endress+Hauser, our devices have wizards in there. So there are wizards for commissioning, but there are also wizards for proof testing. And this makes your life a bit easier because you will be guided through a proof test, one-to-one to the safety manual. So this is a complete proof test or a correct proof test. It will guide you and you will then also get a documentation on this. And this might save you some time in your daily work or in your maintenance schedules. And last but not least, in those devices, we have a second current output. And with this second current output, you can, let's say, play a little bit. For example, here you see foam. We can actually use the second current output to see foam building up. So we can then actually set a threshold with the second current output. And whenever you reach the threshold, you put in automatically anti-foam agent, for example. We had one case in Switzerland. This was a chemical wastewater tank where we did this, and this saved around 80% of the costs of anti-foam agent for the customer. So it's just, you don't put it in every hour, but you only put it in when it's really needed. And that's the good thing here. And this is the offering also that a guided wave radar can give you. Let's come to the takeaways. Well, this was one of my initial slides. Guided wave radar is a problem solver in demanding applications, especially in the oil and gas industry. There are some features within our guided wave radars which can really make your life easier. So you've heard about the gas phase compensation, you've heard about the end of probe recognition, but we can also detect foam, as you've seen the slide before, and we can also detect buildup. And this should support you making your processes safer, but also more reliable and efficient. So this is really interesting features in there. Yeah. Another thing is there that you, and this is what Rob also clearly mentioned, you don't want to have too many holes in your tank, right? But with a guided wave radar, if you think about separators, it might be enough to put one guided wave radar in there to measure the level and the interface. Or if you want to measure the level and foam, you can just use one device. And if you have big emulsion layers, we have even a multi-parameter version with capacitance probe and guided wave radar in one device. So you don't need to put in two devices. Yeah, I told you this second 4 to 20 milliamp output, which can support you measure, for example, level end buildup, level end the interface level, or also level end foam. That's cool, super. But besides this, for sure, we also offer out all the typical digital outputs that you need in bigger projects, like Foundation Field Bus, like Profibus PA. This is also available within our Endress+Hauser product selection. And now let's come to the last point. I've stressed this topic, mechanical level instruments. You can replace them with a guided wave radar with minimal adaptation. In many cases, you don't need to adapt anything. And these will help you then to make, to reduce the maintenance, for example, and also to make the processes safer with the benefits that you get from an electrical instrument, let's call it. And with this, I'm at the end, and I hand over to you, Janish.
Thanks a lot, Matthias. Let me test the knowledge once again of our colleagues. So let me launch one more poll for you. Radar accuracy, is it influenced by the gas phase or not? Okay, so please go ahead and answer this question. So you got another 20 seconds to go. Last 10 seconds to go.
Your watch goes fast, Janish.
Yep, and the watch goes faster than this, yeah. All right, so with this, I will close the poll and I will share the results with you guys. It's a mixed bag.
Ooh. Well, the answer is it is influence, so it's false. And the reason for that is that when certain gas molecules and water molecules, steam is one of those, but also ammonia and also some hydrocarbons, when they are being put under high temperature, high pressure situations, they become polar. Now, what does that mean? They're not getting cold, you know, polar bears or something. But what happens is that they start absorbing and slowing down high frequency electromagnetic waves. So suddenly your level seems to be further away or lower in the tank or in the bypass than it actually is. And this is a dangerous situation. And this is dynamically. So when you have, you know, whatever, 20 pounds or 50 pound steam or something like that, it's not a big issue. It's not a big issue. But if you go to higher temperature, 300 C steam, you know, then 200 pound steam, then it becomes a big issue and it's dynamically error. So it's not like, oh, put an offset in and done with it. No, it's gradual. So you really need to start compensating in order to have a very accurate measurement in those kind of applications where you have these gases. And steam and ammonia are two, and also some hydrocarbons are very notorious for this behavior. So yes, it's false.
Excellent. Let me just put one more question through. And if you have questions, I'm not the only one who's going to ask questions. So you can also ask your questions in the question area. So while you think of your question, let me share one more quick poll. Signal strength is stronger in general from a guided wave radar than from a free space. What do you think about it? Is it true or is it false?
We're talking about strength, huh? Not
Yes.
accuracy.
Yeah, signal strength, exactly.
Yeah.
So last 20 seconds to go. 10 seconds to go. So I see that last minute voters are coming in. So everyone's completed voting, let's say, and I'm going to share the results now. So,
Yes, I think people paid attention. And the reason for that is that you focus all that energy within a foot or 30 centimeters around that rod. So you emit a high strength density signal around that rod towards your level as well. And even if you have some turbulent surfaces, your signal strength from a guided wave radar is way more stronger and so available than a free space radar. Again, it has nothing to do with accuracy. It's availability of signal. And in order to have a device working well, you need good availability of reflection signals. So yes, most have it right. Perfect.
Excellent. Now I will go to the questions which are asked by the participants. And the first one goes like this. What happens when the probe is grounded?
Shall I take it, Matthias, or do you want to?
Take it, Rob. It's fine. Take it.
Okay, I'll answer this one. What happens is that you saw on that picture that end of probe bleep at the bottom of the probe on the right-hand side of the line. So it has a positive reflection. When you start grounding the probe, it actually becomes negative. Now, for the evaluation, it does not matter, but you need to tell the unit that the unit is grounded in order to start evaluating it with a positive blip or with a negative blip, and that's it. So what happens when the probe is grounded, Peter? Not much. The evaluation works the same way, but it has to do with different signals. Yep.
Excellent. The next question is, what is the best way to mount the guided wave radar, in bypass or on top of the tank?
Me or you, Matthias?
I can start. You can add.
That's
so
fine.
I would say it kind of depends. I mean, it always depends on what is available. In many cases, you only have a bypass, then you go with bypass. But if you have the chance to mount it on top of a vessel, this may also be good. I mean, bypass has certain advantages when it comes to maintenance and stuff like this, right? Rob, what would you like to add?
Yeah, I fully agree with you. It's in general, let's put it that way. In general, I like to stick it directly into the tank and not in the bypass. And there's two reasons. First of all, if you go into a bypass, you always have these pipes that lead to the bypass. So it's always very important that you mount that bypass as close as possible to the tank as possible, because in that pipe you cool down your liquid. So the density of your liquid in your bypass might be a little bit higher than in the tank itself, leading that what you measure inside of your bypass is not the real measurement in the tank itself. So when you can stick it into the tank itself, that would be the best way to do it. However, if you have a lot of buildup or turbulence, or you need to do some maintenance because you have a continuous operation, and so on and so on, these are all big benefits of bypasses. But from a measurement technology, representation of the measurement signal itself kind of view, I would stick it into the tank as much as possible. Yep.
So we still have a few questions. Let me quickly get to those, and maybe we give a short answer to all of them so that we can go through all the questions. Is the second output for foam second echo distance measurement, or using the signal strength? Maybe I can quickly answer this. You can actually assign the second current output to any variable. You can even mention the echo strength, echo distance, foam interface. There are multiple things you can assign it to. Anything you want to add, Matthias or Rob?
Yes.
Yeah, Rob, go ahead.
Please be careful with foam, guys. You can measure the foam when the foam is consistent from an electrical property, so dielectric constant perspective. Now, how often is that the case? So it's probably better to use it and set it on the signal to noise strength of the reflection signal coming from the foam, and then you can determine how much foam you have roughly, but it's more to control your anti-foam in that case than to know how much is in it.
And this is something that you really have to set to your process and your application. This is nothing that we can from a factory say, okay, if you do it like this, then it will work, but you really have to see your process and the foam you have in this specific application.
But a good question, Paul. Very good question.
We will quickly go to the next one. Can you share some wrong installation practices and their consequences?
I gave some, and I think Matthias also gave some. One of the biggest things is that people take a guided wave radar, even buy a calibration certificate from the supplier, stick it into the tank, wire up the 420 milliamp, and walk away. Don't ever please do that. Always set span and zero in the tank or bypass where you mount them. That is very important for the performance and for the accuracy. That's one of them. The second thing is, please be very, very careful with flows inside of the tank and sticking a rod or a cable in there. Make sure it's tied to the bottom, or that you get rid of lateral forces. Matthias, you want to add some?
Yeah, I mean, last one, what comes to my mind is, yes, if you have a lot of buildup, be careful. But you've seen the example, right? So these are the typical ones.
Yep.
That I would say.
Let me take one of the last ones right now. Does EOP apply to all guided wave radar level instrument, or is it a unique feature only from Endress+Hauser?
We own the patent, so yes, it's a feature from an Endress+Hauser device. You actually, like I said in the presentation as well, you get a redundant measurement principle on the same rod without you even knowing it. Matthias, now I think about it, I think we should raise the prices a little bit. No,
end of probe,
but it's not your game.
Price adder.
Yeah,
no, but
EOP is in all devices and you get it for free, so it's good.
Excellent. We have run out of time, but our participants are still asking questions, so I see they're still interested to get answers to their questions. So let me go to a couple of them there, because our participants are still there to hear out their question and answers. If I have one hard output in the guided wave radar, could I read from the device level and interface, or do I need two outputs from the radar to do that?
You want to take that, Matthias?
That's fine. Go ahead.
Okay, so the answer is no. If you take a heart means you have a primary value, secondary value, third value, and a fourth value that you can actually use a heart ripper and get 4 signals out of the device through heart, and you don't need a secondary 420 milliamp output. But most customers in the oil and gas industry have 420 milliamp input cards on their control systems. That's why we made it secondary 420 milliamp, because it's a lot cheaper than having a heart ripper generating 4 outputs from the heart signal. And heart normally is not so fast either. So if you have fast changing applications, it might not be the best way to do it either. But so the answer is yes, you can.
Okay. The next question is, in a freestanding atmospheric storage tank for crude oil, what is the probability of having an emulsion layer?
Small. very small.
Okay, let's go to the next one then. So a small emulsion layer is possible. How is the buildup detected? And how is the second 4 to 20 milliampere output parameterized? So how do you configure it?
That's a very good question, Peter. Remember, I was talking EOP. So if you have buildup on the probe, then the buildup will slow down the traveling speed of the radar on the rod or the cable. So if the level shows lower than it actually is, you probably have some buildup on the probe itself, and that's how we detect it. So that's why that EOP signal and setting that EOP signal after you shorten or lengthen the probe is so important, because a lot of functionalities are based on that EOP end of probe signal. Very good question. I think Peter gets it.
Excellent. What happens when the sensor is isolated from the tank? I think, Rob, you like this question. Huh? What happens when the sensor is isolated from the tank via a plastic flange? Is the signal affected by this flange?
Yes, it is. You will lose some signal to the outside because it can emit through the plastic to the outside. It's looking for ground. It's always looking for ground. See it as a hungry signal running on that rod or cable, and is looking for ground, a ground level or ground potential. So yes, you will lose some signal. That's why it's probably smart to pull a small wire from the metal flange of the device to the tank, the metal piece of the tank itself as well. Now, you can still use a guided wave radar in a plastic tank. No problem at all. No problem at all. But your signals will be a little bit less strong, not accurate. It has nothing to do with accuracy, less strong than if you would have it in a metal tank. I hope that helps a little bit. But it will work. It will work. But this is what you can do to strengthen your signal and to make sure that you have a good working application. So.
Excellent. Very quick answer. Is this radar, the guided wave and the free space, is it suitable for SEAL 2, SEAL 3 applications like storage tank, overfill protection, etc.?
Yes, it is.
Yes. Okay.
Short
Excellent.
answer.
Short answer, yes. I think you shared it in your slides as well.
Actually,
IEC
it's in the slides
508 compliant.
Developed according the norm, and yes, it's suitable for that.
Then there's a question which I'm not able to get, but I'll try to ask this anyways. Do we face any distance-related issues regarding guided wave radar?
Do you want a theoretical answer or do you want a practical answer?
Go for a practical answer.
I'll go for a practical answer. Yes, there is. If you want a rod which is whatever 20-30 meters long, hanging on a process connection in the top, yes, you could do that. No problem at all. From a TDR perspective, it will work. No problem. I mean, TDR comes from a technology which was developed to measure changes in soil, and that would go hundreds of meters long or deep. But is that practical in a tank environment? The answer is probably no. So are there limitations with regards to length? Yes, but they're not from a guided wave radar technology perspective limitations. It's more about mechanical transportation, packaging and shipping kind of limitation, the case. Yep. Does that answer it? Yeah.
Yes, excellent. I think we had a lot of questions. In fact, I see that we have run out of time. And with this, I think we have nearly covered all the questions. There's one more which has come up. Maybe we have time for just one more. Do we need two different radar antennas for both tank gauging level and for safety overfill protection? So I think it still goes in the discussion of SEAL 2, SEAL 3.
I don't get the question so much, because if you, why would you have one electronic and two antennas with a safety function? I think that's very dangerous, because if you have one antenna and two devices on the same antenna, you're not very safe, because if that antenna builds up, you have a systemic issue. It's not working. It is working, you can do that, but it's not safe. So I would not go that route. If safety is a device by itself and should never be the same measurement technology as the primary signal itself. Should always be a different kind of technology, preferably, and in a different position as well, to make sure that you do not have systemic issues with your safety in your continuous measurement device. I think it's very dangerous. Would never do that.
A good answer, Rob. It's very important to have a safety understanding as well, and it's also mentioned in the API 2350 document.
Yeah.
And I can only mention, Wilmer, that if you want, you can download this document on the endress.com webpage as well. So you get to know all the details of implementation. We will, in fact, have one webinar on this topic as well, online seminar, which you are attending right now. Any last words from you, Rob and Matthias?
Well, first of all, I thank everybody for their attention. We're a little bit over time, so sorry for that. I think it's you are to blame, Janish, for that.
Okay, I accept it.
No, but seriously, there was a lot of attention, a lot of questions. Thank you very much for your attention. Please stay safe, and hope to see you next week.
Excellent.
Yeah, and also from my side, thank you very much for taking your time. I hope we brought some benefit or some new knowledge for you. And stay safe in these days. Huh?
Yeah.
Thanks.
Excellent. Matthias, I would just like to mention that next week we are going to have an online seminar on the topic of temperature engineered solutions, which is a very important measurement in case of a refinery and other applications as well. We have a very good speaker who will manage this for us next week. Just one housekeeping: if you want to download this presentation, feel free to download it from the handouts which you see on the GoToWebinar panel. If you still have any more questions, and if we have missed out your question, we will answer them offline. And with that, I would like to say stay safe, and see you next time, maybe in a physical seminar where we would like to discuss these topics. This is Janish Kiwala signing out. Hope to see you again soon in real life as well. Excellent. See you again. Ciao. Bye, Matthias. Bye, Rob.
Bye.